So I welcome you all to this webinar on quantifying vegetation dynamics for designing and managing nature-based solutions. And this webinar is part of a series that is organized by the Strategic Research Team of Deltares on Sustainable Solutions. And in this research program, we have 4 target areas, and each of them will host a webinar. So there's the beneficial use of sediments, the nature-based solutions. We're talking about circularity and sustainability tools, and about national and international mainstreaming of sustainable solutions. So today we're talking about nature-based solutions. And of course, the question is, why is it a priority? Well, as you all know, we are currently in a very important weeks in which in Glasgow, there's large talks about what to do about climate change and which policies can be implemented in order to reach this. At the same time, the UN has been, after a decade on biodiversity, now launching a decade on ecosystem restoration, because we see biodiversity decline is a major cause of concern. So climate change and biodiversity have also caused the EU to define the Green Deal, an important strategy to reach climate neutrality by 2050. And not only that, it also strives to have affordable, smarter solutions, environmentally responsible projects, and a farm-to-fork strategy. Now, this is James V. Bruce, and he is a Canadian hydrogeologist, and a famous quote from him is, "If climate change is a shark, then water is its teeth." So today we're talking about nature-based solutions for water-related challenges. And in this document, which is a future brief that was launched by the EU in February 2021, there's an interesting quote that says nature-based solutions are our best ally in fighting against climate change and help deliver the EU biodiversity strategy for 2030. These solutions bring multiple benefits. They empower people and communities, and they increase resilience, and they provide jobs and business opportunities. So scaling up our investments in nature-based solutions and stepping up their implementation is the best insurance policy of them all. Also, the IUCN has been making a very well-known definition for nature-based solutions and says these are actions to protect, sustainably manage, and restore natural or modified ecosystems to address societal challenges effectively and adaptively, simultaneously providing human well-being and biodiversity benefits. So if we're talking about the nature-based solutions, if you really want to specify it a bit more, they normally make proactive use of natural processes. Now, they're also sometimes called building with nature. In the past, also the word eco-engineering was used a lot. And in the urban environment, there's a lot of talk about blue-green infrastructures. And all of these nature-based solutions, they are there to tackle water security challenges, such as flood defense, but also flood and drought mitigation and adaptation, environmental pollution, or urban heat stress and climate adaptation. And all of this, of course, to reduce risk, we also want to be adaptive over time and to provide cheaper or better or quicker alternatives to the traditional ones that we have been used to before. Now, nature-based solutions often serve multiple goals, taking stakeholders into account and different objectives. Often they also are being used in order to avoid lock-ins that can be existing if you take a hard structure that is difficult to change after a period of time. And nature-based solutions, they cover all stages in the policy cycle. If you want to implement them, we start at the top with system understanding and the assessment of the issues at hand. And then once you've understood it sufficiently well, we're talking about designing and assessing what is the best solution and making the decision on how to implement it. So that afterwards, you go to the phase of construction and implementing the nature-based solution. And once it is there, we have to monitor it, but also to maintain it over time, because nature-based solutions are dynamic over time. So we have to understand that dynamics well. And in all of these 4 blocks, it is very important that we realize that this is a multidisciplinary undertaking. So it is not only the physical system that we're working with. There's also the social sciences for all the people that are living within that area, and the ecological aspects that interact with the physical system. So today we really talk about the knowledge on ecosystems and their dynamics and why it is important to have that. Because you need to understand what's happening. Why is it happening? So for example, this is a little picture on the right-hand side on the top about alternative stable states. So if there's a tipping point that might cause a system, an ecosystem, to shift from one state to a next, it is important to realize that this may happen. But also if we are designing a nature-based solution, what can we expect? And do we not have unrealistic expectations either? And when we are constructing or implementing them, what can we do to influence the construction? Can we make it as environmentally friendly as possible? And afterwards, in the monitoring and the maintenance, we really need to take care about how it is developing and whether perhaps adjustments are needed. But they are flexible and they're adaptive, and this really helps over the long run. So if we're talking about quantifying that system understanding, there's various ways that you can do that. Of course, you can go into the field to try to understand the system by measuring, by taking readings, but at the same time, some things that you might not be able to find in the field. So you might go to a large scale model or an experiment, such as that you see on the right-hand side, where real vegetation is being tested under extreme conditions in a wave tank in the delta flume here at Deltares. Because these extreme events you might or you hope not to find in real lifetime in the field. But next to that, there's also the modeling. And also these three together, they give you a good, proper, quantified system understanding. Now today we really focus on modeling because modeling allows us to upscale in space and in time to address future scenarios and to also see what the impact is of design choices on the response of the overall system. And in this webinar, we are taking you through various ecosystems. So we'll start with Koen Berends, and he will be talking to you about how to quantify riverine ecosystems and the nature-based solutions therein. That will be followed by Jasper Dijkstra, who will take us to the salt marshes and developments over there. And then we move to the mangrove systems with Uwe Best. So with that said, I would like to give the floor to Koen Berends to talk about the riverine system. Koen, nice that you're here. Go ahead.
Thank you, Alice, for this nice presentation and introduction. Hello, you all. I am excited to talk to you today about vegetation modeling in rivers and streams. Before I delve into a bit more detail, I want to discuss why riverine vegetation is important. Because it affects the entire system, and therefore it's an essential tool. For example, aquatic vegetation may grow in the stream and increase its flow resistance significantly, which affects flood risk on the one hand, but may also be a useful tool to prevent droughts. Riverine vegetation, riparian vegetation, prevents or has biota for habitats, but also affects the morphological evolution of a river. And of course, people that live close to the river probably enjoy large biodiversity in their backyard. So today I want to talk to you about riverine vegetation. But I cannot tell you everything, so I'll just focus on three trends that we're working on with our partners. And these trends are river vegetation dynamics, remote sensing, and flexible or natural vegetation. What you see here on this picture is the Leiga, which is a small stream in the Netherlands where we study the effect of aquatic vegetation on flow resistance. So in small streams, the growth of aquatic vegetation may lead to a rapid increase of flow resistance. And this may lead to a problem for flood risk. We found in our research that traditional ways of dealing with this flow resistance, for example, lab-based vegetation formulas, are inadequate. And therefore, we turn to a data-based approach, where we couple a data-based resistance formula with a dflow1D hydraulic model. On the right, you see a figure of this research, where the red dots are the resistance over time, and the bands show the prediction of the Manning coefficient. Now you see that at one point, the vegetation growth increases, and then suddenly it no longer fits, and this is due to human intervention. So this tool allows us to assess the impact of human intervention on streams. In larger systems, such as this river, this is the Allier River in France, the evolution of riparian vegetation determines the morphological evolution of a river. For these type of systems, we're not looking at annuals that have a growth and decay cycle within a single year, but perennials, which develop over multiple years and experience multiple growth and decay cycles. Understanding these type of dynamics are very important to assess the longevity of nature-based solutions. What we see here on the right-hand side is a model result from the Riverine, the riparian vegetation model by Dr. Meike van Oorschot, where the colors denote the more red is an older plant. Data is very important in modeling large-scale rivers, and therefore it is also important to know where certain types of vegetation are distributed in the floodplains. We're working with various partners to use various remote sensing methods to classify vegetation maps, for example, from satellites, from planes, or from drones. What we see here on the right-hand side is an example from a Korean flume, where we try to assess the distribution of aquatic vegetation, so vegetation below the water table, using multispectral and hyperspectral imaging. These spatial vegetation fields can be used in software like DFlow-FM or Delft3D Flexible Mesh to allow us to quantify the effects of distributed vegetation in rivers. An example of such a tool that can be used in practice is the vegetation monitor, which is aimed at on-the-fly classification of satellite images for the distribution of riparian vegetation in floodplains. So what we see here, for example, is the floodplains near Deventer, a city along the Dutch River IJssel. And we see the classification of those satellite maps. Finally, I want to talk to you about natural vegetation. What we see on this picture is a photograph of the River Experiment Center in Andong in South Korea. And it is in this facility that we, together with our partners, the KICT, study the effect of natural vegetation on flow and sediment transport. What is important to understand is that while vegetation formulas that are based on rigid cylinders are certainly effective and that prove their value, that real natural vegetation does not behave like rigid cylinders. Real vegetation deflects and it reconfigures with the flow. So we're working with partners like at Aalto University to validate the implementation of natural vegetation formulas in Delft3D for use in hydromorphodynamic simulations. So I've talked about three trends in riverine vegetation modeling, which is vegetation dynamics, spatial distribution using remote sensing, and flexible vegetation. But it's important to understand that all these new trends are backed with experimental data and field experiments. So what we see here are a few examples where we and our partners are in the field gathering those data that are so important to assess the validity of our methods. If you're interested, or perhaps you like to collaborate with us, please do not hesitate to contact us. And thank you so much for tuning in.
Thank you very much, Koen. It was really interesting to hear your short talk. We will now move from the river system to the salt marshes, and I'd like to invite Jasper Dijkstra, who will tell you a bit about that. Go ahead, Jasper.
Yeah, thank you, Alice. Indeed, I will talk a bit about the salt part of nature-based solutions, salt marsh dynamics, in relation to their creation and restoration in a coastal management context. So why do we want to manage salt marsh functions? Well, as Alice already mentioned in her introduction, they have a lot of functions that we need or appreciate. Flood risk reduction is an obvious one. There's habitat provision, duck biodiversity. Less known functions may be nutrient, carbon cycling. It can be a sediment sink in estuaries that have a lot of sediment. and that hamper life below beneath in the water, and they have, of course, a recreational function. And these are all related to the performance of a marsh. But this performance will change over time because the size of the salt marsh and the layout of the salt marsh will also change over time. Partly, of course, due to sea level rise, we all know, but also other factors are changing, like sediment supply. The wave climate will change over time, probably, as things get more stormy, perhaps. And well, vegetation is a natural thing, so it's dynamic by nature. And to quantify, to be able to assess the performance over time, we need to be able to see how a marsh develops over time, to see whether the performance is still sufficient in the year 2050 or even later. Ideally, in a coastal management context, we want to quantify the effects of nature-based solutions so that we can do a cost-benefit analysis. We don't want it because it's natural. We want it because it has a good cost-benefit ratio. So we need to be able to quantify both costs and benefits on the long term, and that makes it. Once we know those, we can think of adaptation pathways approaches, as illustrated by this figure, where you see some pathways will run a long way into the future, because the time is on the horizontal axis, and some lines, like the orange, yellowish one and the green line, they may be okay for a couple of decades, but then they terminate. So in order to assess which track is the best one, which development scenario offers us the best costs or the best benefits, we need to be able to compare different scenarios, and models are a nice tool to do that. And models are also a nice tool to provide stakeholders, not only managers, but also people that actually use the area, live next to it, use it for whatever reason, to give them more information on how should we deal with this area, and what happens if we turn a bit on this and twist a bit on that, and see what are the consequences of management actions to an area. So that's something we can do with model, to say, okay, this is how your marsh will develop under certain management scenarios or changing environments. And the nice thing of a model is it quantifies both spatial and temporal change. It's not straightforward, because especially in these systems, there's a lot of physics and biology both involved. And we have a long history of developing physics-based models. And there's also a long history of ecological models, but only recently they started becoming more combined in order to be able to do studies like these. Of course, you need to have those biophysical feedbacks integrated properly. More about that later. And the reason for doing this, you could also say, okay, we know a lot about the coastal system already. We've done lots of measurements, and that's all true, and it's very welcome, and it's good knowledge. But under change, you can wonder how applicable are those empirical figures that we already have. And that's illustrated by this figure. It's a study done on the function of a salt marsh. The delta HS you see in the figure is the wave attenuation over time. And in the upper part, you see what happens what may happen in Louisiana as a result of considerable vegetation change. Marshes are drowning there, even under a relatively positive accretion rates. But in the lower figure, that's the situation in the north of the Netherlands. You see that the function illustrated by the black bands, for example, can either increase over time if there's sufficient accretion, but it may also decrease if there's not sufficient accretion. So having this accretion rate right is a very important thing to see, okay, do we gain or do we lose function over time? And if we just use an empirical accretion rate, which is constant over time, we know, okay, it's an estimate, but it's not really applicable to what we want to know. So therefore, we think process-based models that let those accretion rates, for example, be determined by physical processes that interact with the vegetation are very well. Therefore, we developed this nature-based dynamics model, or a combination of two models actually. There's the Delft3D flexible mesh that we all pretty much well known. We use it to calculate flow, sediment transport, and bed level changes in an area. And we couple it to an open source Python module. Sometimes we call it the dynamic vegetation module, but you can use more species in there, as Uwe will also discuss in a later talk. So the nature-based solutions dynamics tool is a more fitting name. It will be open source on GitHub by the end of this year. If you want to work with it, please contact us. You're very welcome to use it and improve it. And what it does, it calculates the development of a biota, in this case salt marsh vegetation, by seeing where it colonizes, how it grows, so how it expands once it's there, and of course how it dies depending on age and physical conditions, and where vegetation is present, how much it is, and what effect it has on the hydraulic resistance is exchanged via the basic model interface, BMI. And that makes it really quick and flexible so that you can deal with a lot of time scales that play a role in these estuaries. So why all do this complex modeling? Is it really necessary? Well, in some cases, it's not. As illustrated by this figure by Christian Schwartz, there are areas surrounded by the orange circles where there's either a bare landscape or a very stable situation. There's not changing much. So there's no need to employ heavy models to say anything about this. But there are also a lot of situations, the dark green parts labeled self-organization. That's where the interesting stuff happens. A lot of biophysical feedbacks, you don't know beforehand where it's going to go. So that's where you need models to see where things will be going, depending on hydrological, morphological development, but also on the type of vegetation do you have. Does it grow quickly? Does it grow slowly? Factors like that determine what the landscape will look like. And of course, there's the part in Delft3D flexible mesh where you need to represent that vegetation correctly. We do this through drag, hydraulic resistance, and there are various methods to do so. In 1D or 2D, 3D. The simple one is a bed roughness, which we advise not to use too much. But there's also a trackitope approach, a rigid rod model approach. You can do it with flexible vegetation. You can do it for simple vegetation like grasses, but also for complex vegetation like the mangrove illustrated here. And there's not only an effect on flow, but also on waves. So it's fairly complete. And so is the ecological part. One of the things we incorporated in there is the windows of opportunity concept, because the establishment of vegetation on a bare mudflat is a very difficult process, and it's for the vegetation, and it's important to get it right. So there needs to be a period with a lack of physical disturbance so that the vegetation can take root, grow, and develop. And this is, for example, we worked with this on the Marconi salt marsh, which is an artificial salt marsh near Delfzijl in the north of the Netherlands, where it was also a physical field experiment where different mixtures of clay and sand were placed to see what would be the best way to develop a marsh. And we modeled parts of it and also tried here on our flumes to see what mixtures provide the best conditions for Salicornia to take root and develop further and prevent erosion by waves later on. We also did a model on a slightly larger scale in the Western Scheldt, in the southwest of the Netherlands. This is a model study by Pim Willemsen et al. To be published fairly soon, we hope, where we looked at two marshes basically. One is exposed, so relatively high waves, whereas the other is sheltered from the typical wind conditions. And we studied the landscape development there, what you see illustrated with the yellow part, the lower part of the screen. If the waves are really low, you get a tight dominated landscape with a lot of channels and some patchy vegetation at the front. Whereas if the waves are really high, so the lower panels, you get a very wave dominated, straight, fairly boring landscape with a lot less salt marsh extent. So that means that the physics we expect do play a role on the extent of the salt marsh. And it also means it can be managed. If you manage to decrease some of the waves acting on your salt marsh, you probably get a bigger salt marsh. And the same actually applies to changing sediment concentrations. So in the Western Scheldt, it's not the case, but in some estuaries, you may have a dam that cuts off the sediment supply to the estuary, for example, and that will have its consequences on salt marsh or mangrove development, perhaps. So this is also a way to link individual nature-based solutions or local nature-based solutions to the larger system and see how they interact, and to see how you get enough functions through your entire system that you're trying to manage. So that's my part on salt marshes. If you want to know more, here are contact details, and it's been a pleasure.
Thank you very much, Jasper. Really nice to hear something. If you have any questions to the speakers, by the way, in the Q&A on the website, you can type in your questions, and we will try to discuss them after the presentation that Uwe Best is now going to give. So Uwe is going to take us to the mangrove systems of Guyana. Go ahead, Uwe.
Thank you, Alice, and good afternoon, everyone. From the discussions for the COP26 conference, we learned from the IPCC that the recent regional assessments of the climate impact drivers, so the CIDs, such as the mean temperature, droughts, coastal flooding, and coastal erosion, are all expected to increase in frequency, and they're going to become more prominent and more widespread in the next 29 years. And so this is a conclusion that is not in the distant future. It isn't an imaginary thought that we can have to pass on to the next generation, but it is something that will impact our generation and our livelihood. And so your presence in this meeting really speaks to the importance of not just translating the science for coastal adaptation, but really translating the lessons learned into definite management options. And so as a coastal engineer, any protection measure is required to meet the safety standards with respect to wave overtopping, wave run-up, as well as coastal erosion. And it's expected to do all of this while maintaining some integrity structurally. And so for many countries, the primary mode of delivering on that is the use of hard structures, such as dikes and seawalls and groins. But as the presenters mentioned, vegetation and focus of this presentation will be primarily on mangroves. They provide numerous ecosystem services, which all increase the coastal resilience of any country. And so the proposition for today will be one of a green-gray solution. And green-gray solutions can take many forms. In Guyana, the mangroves are often combined with concrete dikes, but in Indonesia, you have the mangroves being combined with permeable fences and bamboo groins. And the reason for this proposition really lies in the fact that we should capitalize on the cost savings with respect to the reduced design and construction costs, as well as the maintenance costs. And so when thinking of these green-gray approaches, the bottleneck is really about how can we adequately quantify the ecosystem services across a specific belt width. And we do that even thinking of sea level rise, so the rising water levels, thinking of higher waves, as well as thinking of the stormier conditions that will face not only parts of Asia, but as well as the Caribbean. And so we have to realize that the natural system will have a large amount of variability. and it will have an associated tipping point. Here you can see two mangrove fringes in Guyana. Both were part of the restoration works, but the figure on your right-hand side shows a system that is at its tipping point because there are changes with regards to the sediment input, the wave energy, as well as the amount or volume of sediment being lost from the overall system. And so despite of all of these, despite of the high tolerance, you still have these tipping points that exist. But equally so for hard structures, the figure below shows failure in the primary dike, and this is a structural failure as well as a failure that was compounded by overtopping that resulted in the repeated flooding of the coastal hinterland. And these are all areas that are within a few kilometers of each other. So I say all of this to say that the need to understand, adapt, and build with nature is an iterative process, and it can be optimized through the use of numerical modeling software such as Delft 3D. And so piggybacking on what Jasper said, we used a similar approach for the coupling, whereby we coupled Delft 3D flexible mesh with the establishment, growth, and the decay patterns for the vegetation. And this spanned a maximum of 160 years. And with it, we were able to adequately look at the data that was needed to develop the model for the Guyana area. And we used the transect shown in the figure to capture data with regards to the water levels, currents, the wave heights, as well as to fine tune and define the sediment parameters in Delft 3D flexible mesh that are really critical towards the modeling of these cohesive coastlines, such as the concentration, your velocity, your density, and most importantly, or uniquely for me, is that during the field campaign, we were able to translate the vegetation parameters with regards to the density, the height, the diameter of not only the trees, but of the fumatophores, so the small roots. We were able to translate all of these into a vegetation coverage parameter that was defined at specific points across the submerged depth. And so at the end of that, we have this coupled model that allows for the interaction between the intertidal flow, the waves, the sediment transport, as well as the spatial and temporal changes in the vegetation. And so this simulation spans about 160 years. And if you really look at it, you can clearly see the establishment, the growth and the expansion of the mangroves, but equally so you can see the patterns that develop with regards to the inundation stresses, the competition stresses between the actual plants themselves, even though it's a single species model, and more so the erosion stresses. And so at the end of this, you have a system that is able to develop to some sort of dynamic equilibrium. And you can see in the higher areas, the bed level has increased beyond an amount to allow for the suitable inundation of the mangroves, and so they're outcompeted by terrestrial plants. Moreover, we were able to do a combination of multiple species, which I think is quite novel for the approach. And this included not only the Avicennia, but also the Rhizophora, as well as the orange mangroves. And we looked at a tide-dominated area in Japan, and you can see the transformation of the mangrove species if we're now thinking of just the inundation and competition stresses over a period of 100 years. Now, when we move towards a wave-dominated environment, we saw from our simulations that waves are quite critical towards moving the sediment towards the mangrove fringe. So it's a key process that is important for the accretion within the mangrove fringe itself. And so what we try to do is to partner with Conservation International on a recent project, and we were able to then translate the discussion from, okay, mangroves can attenuate waves, but to provide something meaningful, whereby we were able to determine the mangrove belt width that's needed to protect a certain area, depending on various scenarios of wave heights. And what is clear is that even the smallest inclusion of mangroves can have a meaningful impact, a meaningful benefit for that coastline. And if we compare to the typical hard solutions or soft solutions that are more permeable, we can see that the use of mangroves, whether it be the planting or the maintenance and monitoring, is quite cost effective. So if we were to move the discussion to sea level rise, we can see from scenarios using not only the IPCC but also the NOAA approximations that the tipping points for these systems often occur when the water level has exceeded 2.3 meters. And this is quite important when thinking of the protection of many low-lying coastlines with regards to the impacts of the coastal flooding and everything else with regards to sea level rise. But in the simulations, we were also able to see that the system is able to keep up with the sedimentation rates despite the increasing inundation stresses prior to these tipping points. And so there's a clear relationship between the sedimentation and the inundation patterns. And what is even more important is looking at the below ground biomass, because we saw that systems that were characteristically high with regards to the below ground biomass storage were able to ensure the survival capacity to be a bit longer, but still these tipping points exist. And so if we now translate all of these conclusions into something that is more managerial, we can think of either increasing the fringe width, looking with regards to maximizing on the benefits of having the mangroves there, either using sediment trapping units, permeable fences, permeable groins, but we can also think of increasing the resilience of the coastline itself, especially for many low-lying areas where it's impossible to imagine just having mangroves as the only form of protection. And in Delft 3D Flexible Mesh, we've been able to include and monitor the effects of having several of these solutions being implemented, not only in Guyana, but also in the Indonesia project. And so just being able to combine this with a cost analysis, you can have an ideal solution to then implement. And so the takeaway messages for today should first and foremost be that mudflats and mangroves have a high wave dampening capacity. Being able to include both single and multiple species is possible within the Delft 3D Flexible Mesh approach that Jasper spoke about. And knowing that in every system, there is a large variability in the physical processes that govern the overall development is key, and utilizing numerical models as optimization tools is quite useful. The long-term monitoring of the hydrodynamics and the morphology is critical for any sort of management strategy and practical works. And knowing that green-gray solutions, the implementation of green-gray solutions is quite helpful with regards to reducing the net erosion and coastal retreat patterns. And so the incorporation of these approaches can then be added as an additional layer in Delft 3D Flexible Mesh. And so we can have clear conclusions on not just understanding the natural system, but knowing how we can protect and create a sustainable approach. So thank you for your attention and your questions.
Thank you very much, Uwe. Really nice to hear this. We are now going to the Q&A part of this webinar. So if you have any questions to the speakers, you can place them in the Q&A box on the website. So I would first like to ask Koen to come to the desk again so that he can answer a few of the questions that are related to his presentation. Koen, just to start off with, can you explain a bit on, you talked about the streams and the vegetation in the streams, and how does that then relate to like a nature-based solution approach for these streams?
Yeah, thank you, Alice, for this interesting question. So in the streams, we've been trying to assess the effect that vegetation has on the water levels and on the flood risk. So nature-based solutions is also about sustainable management of these, of vegetation in the systems, and especially in these streams, we know that vegetation can serve two purposes. It can increase flood risk, but it can also help to reduce droughts. So finding a way of sustainable management such that both functions can be met, or that we can at least find some sort of sustainable management going forward. To go there, we need the adequate tools. We need to understand what the effect of such vegetation is, and these type of modeling exercise can really help to give an insight into the system.
Yeah. Now we see also that there are some questions coming in that are related to, do you choose for a 1D or a 2D or a 3D approach in your modeling of a nature-based solution? Can you give a bit of explanation on what the strategy is for that?
Yeah, it's always a good question to consider what's the tool that is suitable for my problem. For rivers, for example, we often think of rivers as these one-dimensional things going through our landscape. And for many solutions, for many problems, a 1D model is suitable. But if you look at nature-based solutions, what we've seen in recent research is that for these small streams, 1D is suited because of the data that you have for your problem, right? So we don't have this detailed 2-dimensional or even 3-dimensional data. And in this case, a 1D approach is suitable. But if you go to a floodplain, to a larger river where the exchange of momentum between floodplain and main channel is important, then you need to go to a 2D approach. And if you're also interested in smaller scale events, perhaps the sedimentation of side channels, for example, where 3D structures are important, then typically for these smaller case studies, 3D solutions are really useful. So it depends on the data you have on one side and on the tool for your problem on the other.
Yeah, exactly. So then thank you very much, Koen. We will go to Jasper. Also, Jasper had a few questions posted. I see a few questions for him as well. But first of all, Jasper, you've been talking mainly about salt marshes. Can you tell a bit more about what types of organisms can be used for these types of applications?
Yeah, well, different organisms. We talk a lot about vegetation, but there are different types of vegetation, like mangroves, but also submerged aquatic vegetation, for example, in both in freshwater systems and in saltwater systems, like seagrasses, but also some animals, sessile animals usually, oysters, oyster beds, mussel beds that you can use as part of coastal protection. And there are also cases where we worked on corals, very different, but also a nature-based solution in many areas. And there's also people that have worked on modeling biofilms, the stabilizing effect of a biofilm hampering the erosion of mud. It's also using this BMI technique to communicate with Delphi flexible mesh.
Yeah. So it's actually quite interesting because we see that the effect of these animals and the organisms and the plants is so extremely clear. So can you explain a bit on why we still often don't really use them in our analysis?
Yeah, that's something I wonder also about. Although when I was trained as a civil engineer, like the years or more well more than a decade ago. It simply was not really in the curriculum. So it's also what we're used to. And of course, we learned a bit more and we realized a bit more. And we value nature a lot more than we did 20 years ago, perhaps. And the other reason is we simply didn't have the knowledge to do it. And we calibrated our models to mimic the behavior. So a part of these effects of nature-based solutions are in our older models, but hidden in some calibration coefficient. And I think now we gained a lot by making the role of biota in coastal and riverine systems much more explicit. So that gives us more tools to actually use those processes to, well, our benefit. And of course, there's still a lot we cannot do yet. I think this is it's a great field of research and development. Yeah, and it's a lot of fun to combine ecology and physics more than that we used to do it in the past. And bring things a step further by doing so.
Yeah, definitely. There's one more question that I see coming in the chat, and it's really a bit more on the technical aspects on where can we find more information. It also seems a bit of looking for training on, especially if you haven't had that in your studies, so to say, that's what you're referring to. Where can people find more information if they want to?
Yeah, I would like to say you can find it right now, but we're actually in the middle of opening this up to a more general public. I think a lot of things you actually need are already in Delft3D flexible mesh. So look at the manual carefully, and you can do what you want to do. But perhaps it's more useful to wait a bit, because we're transforming all these separate tools that we have now. I mentioned coral. There's UW's model on mangroves. There are other models on mangroves. There's a salt marsh model. A lot of that is very similar. So we're boxing it up in a nature-based dynamics tool and that has different ecological cores. So for each system, it has its own ecological cores, but the whole interaction with Delft3D is something you don't have to worry about. So we're working on consolidating that code now on GitHub. And yeah, it's work being done. So I can't share it here yet, but if you're interested in using it, contact us. And part of it will be done by the end of this year, including some manuals and a bit of instruction. Part of it will be done next year, because yeah, it's quite a bit of work. But we're really interested in hearing about you. Okay, this is the type of functionality I need for my project, or this is what I want. Also, your experience as a user are very important to get it further, because we did a lot of development work here and also with PhD students. But it's also time for more people to start using it and tell us their experiences and needs, and as a community improve this tool more and more and get it more applied.
Exactly, because that's what it's all about, right? So thank you very much, Jasper. I would like to move to Uwe. Also, there's a few questions for Uwe. I think it was really interesting that you showed so much of the long-term developments of the mangroves, but there's also a lot of discussions on the impact of, say, extreme events to the functioning of a nature-based solution. So how do you incorporate that into your assessments?
Thanks for the question. Yes, there's definitely a lot of discussion on trying to quantify the impact of these extreme events on mangrove or salt marshes. But the idea is, okay, first, we've seen that the long-term processes that govern the overall development are more key towards the longevity of the mangrove fringe. The short-term extreme events tend to have maybe a limited impact, and if they're of a large magnitude, then of course you would see things like the breaking of the mangrove trees, the uprooting, but these are events that are quite rare, and we lack data to actually quantify what happens and to what degree do we see changes in things like the drag and I guess in being able to really see the interaction with the tidal flow and the waves as the vegetation breaks. So within my modeling approach, we look at the changes in the overall density of the plants within a particular grid cell, and that in some way encompasses the changes as it goes through the effects from higher waves or changes in the sediment supply. But really the combination, I think, as you mentioned and as Jasper mentioned, of really having the model, the flume, and the numerical models with the field studies is quite key, because it really, you need to have the field observations to see what happens in nature, to what extent, and be able to actually quantify that. And it can be further tested within the flume studies, and both of those solutions can then be optimized using the numerical models. So yes.
Thank you very much. It's a really nice answer to the question. And I see a few questions in the chat coming in that are not necessarily related to the vegetation aspects of your study, but also to how you've been incorporating the sediments. Like, for example, what is the difference between using or modeling the more muddy sediments versus more sandy areas, or how does it deal when your sediment is coming in like on a pulse system because of the rivers are providing that in a not constant manner? Is there also ways to incorporate that type of aspects?
So it's quite interesting. We, along the Guyana coastline, I guess the sediment is supplied in plumes in a similar way, because the sediment supply is variable as it travels along from the Amazon River. It travels along in these wave plumes. And so we have captured that in the Delft 3D approach, just varying the boundary conditions and seeing what are the impacts of that. But we have also coupled that approach with a MATLAB-based model that basically allows for the actual representation of the wave plume, if you can say that, for the Amazon sediment. And this 1D model really then informs the Delft 3D approach. So again, I think Jasper mentioned it, it all depends on what you want to model, choosing the best option to actually do that. For the Delft 3D approach, we use a depth average 2D model. And so in terms of running various options, I mean, it's time consuming, and having either a Python-based script or a MATLAB-based script can adequately inform on it. But yes, we have been including the variability in the sediment supply.
Yeah, thank you very much. We are nearing the end of our webinar, and I would really like to thank all of you for your attention. We have gotten many more questions in the Q&A that we could possibly answer in the short time of this webinar. If possible, we will be able to get back to you via email. Otherwise, contact us again if you don't receive any immediate response from us. It was a pleasure to have you here. We are going to continue this series of webinars with the two remaining topics of the Sustainability Research Program line on circularity and on the governance and implementation of nature-based solutions in the next year. If you want to be keep them informed on that, let us know. The dates are not necessarily specified yet, but it will be shortly after the new year. So we are looking forward to seeing you there. If you want to look back to this webinar, it will be posted online soon so that you can have the time to see and to think more. So thank you very much, all of you, and have a nice afternoon. Goodbye.